Hello, everyone, and welcome to week one of Artificial Intelligence. My name is Dr. Alan Dennis. I'll be your instructor for this term. I wanted to kind of go over a few things, and as you can see on the screen, kind of basically our outline and our agenda for this conversation. I'm going to start by introducing myself, give a little bit of background, certain sort of trivia, if you will, and so on. Then we'll go over the syllabus, the things that are expected of you through this course, drill into chapter one, and then follow up with chapter two, and then close with the obligatory questions slide. So jumping right in, who am I? As I mentioned, I'm your instructor. So a little bit about me. I have a doctorate in computer science from Colorado Technical University. My concentration was in big data analytics. It was a field that's always been interesting to me, and I returned to the university after a substantial amount of time. And so it was an interesting experience. I have a master's in computer science with a concentration in artificial intelligence and advanced analytics or mathematical computing from West Virginia University, a bachelor's of business in computer information systems with a concentration in computer information systems from West Virginia University as well. I have a lovely wife, four children that are all adults, three grandchildren, with another one on the way. We live on a 74-acre farm in the middle of literally nowhere. We have way too many animals: cows, sheep, horses, ducks. If you name it, we probably have it or have had it in the past. Looking at the images on the screen, the background image is taken from an angle of the farm. Bottom left-hand corner is Ollie. He's a Munchkin cat. Um, he's in the room with me, so he may make an appearance during this recording. Also, to the right of Ollie is the three grandbabies. The youngest on the far left, the oldest in the middle, the middle one on the right, and the our youngest adult child on the far left. None of the babies are hers, but she's a great aunt. That's me in the middle in the funny hat, taken it to graduation. So it gives you some sense that I'm not exactly young, as does the image you're seeing right now. To the right of that image is the youngest grandson. Last Christmas, we don't have, I probably should get some updated pictures from this Christmas. As you can see, the facial expressions are pretty amazing. He was definitely in stimulus overload at that moment. Bottom right-hand corner is my wife with one of our horses. That is a miniature horse. Her name is Carrot. She was was taken some time ago when we first brought her in. Moving on to a bit more about from a work perspective and research interest perspective. I work as an advanced analytics architect at a company called Avanade, which is a partnership between Accenture and Microsoft, focusing on artificial intelligence, machine learning type problems, typically using cloud computing resources, but not always. Have an interest also and do work with obviously things like machine learning, data platforms, and so on. In general, I'm interested in big data because it is kind of an important thing in today's world. Software development as well, because I think we can always do it better. Education, how we learn, how can we do things in a different way that might be more productive. The Internet of Things, stream processing. My dissertation focused on the types of errors that people make whenever they're encoding the rules that govern complex event processing. Complex event processing is a type of stream processing, not necessarily relevant for this course, but an interesting topic nonetheless. So going on to the syllabus, an important thing that you should spend some time taking a look at because it controls what happens here. Granted, it is subject to change, but I think it'll probably stay pretty much as it is for this course. So from a course description, always a good place to start because we have to tailor the content that we discuss to that course description because it's essentially a contract created between the university and the students as to what these courses are going to be about. So this course introduces students to the fundamental concepts and techniques of artificial intelligence from a computer science perspective. So that kind of means that we need to be a little heavier into the topic than we might be if, say, we were doing this from an information technology perspective or from a business perspective. So we're going to be talking about things like algorithms, probably going to see some math, bit of statistics, and so on. The emphasis of the course will be on the selection of data representations and algorithms useful in the design and implementation of intelligent systems. So there's several key things there. Data representations, that's kind of about knowledge representation, state representation, and so on. Definitely something we'll spend a fair amount of time talking about. The algorithms we'll also be talking a bit about. Uh, and then moving on to the last sort of description, this course will introduce an AI language. In this case, that language is going to be Python, and discuss its application to AI methodologies. So your assignments that you'll be doing, which we'll talk about here in a moment, will be written primarily in Python. And the motivation for that is that Python is a very popular language. There are lots of frameworks that are or can be utilized by it, and it is in the AI space probably what most people are using these days. Um, Learning outcomes. So you will successfully complete this course if you can, at the end of it, describe the fundamentals of AI, demonstrate capability to apply appropriate search techniques. So we're going to have to talk a little bit about search. That's clearly outlined by the learning outcomes. Understand the key concepts of knowledge representation and reasoning. Definitely going to talk about knowledge representation and reasoning. Although interestingly enough, that's not something that a lot of other artificial intelligence classes focus on these days. A lot of the emphasis is shifted over to very much connectionist approaches with things like neural networks and deep learning and convolutional neural networks. Implement a simple learning system using appropriate techniques for a given problem domain. You would definitely be doing that. One of your assignments is to do some learning and some searching. Articulate the distinction between techniques for information retrieval, language translation, and speak recognition. We'll definitely cover those topics as well. Program, navigate, and control a robot. You'll be doing some research into that topic. You're not going to build a robot, but you will be doing some research into robotic simulation environments, something almost the same thing. Moving on to papers. In general, there are 4 papers in this course. The expectation is that you will use APA 7th edition. Do review the rubrics. They do outline what I'll be looking for as I grade. They'll be roughly 2,000 words. You'll need at least 4 sources, probably a few more, and those need to be peer-reviewed sources. It means that they're scholarly in nature and have been through a peer review process. Generally, journal articles that are peer-reviewed, whenever somebody wants to publish in those environments, they must submit their draft of their paper, oftentimes in an anonymous fashion without their name on it anywhere. Goes out to people that are in the industry or in the field that are familiar with that topic. They evaluate them, provide feedback. The author is then expected to incorporate that feedback. It goes potentially through another round of review and then gets published. It doesn't just get published without somebody looking at it and making sure that it seems like it is real and appropriate. Your papers will be on knowledge representation, decisions, deep learning frameworks, and robotic simulator. So you'll basically be looking into robotic simulation environments, and we'll talk more about those as we get closer to them. Projects, the other element of this course. Uh, the basic idea here is that you give a proposal for a project. Once I approve it, you implement it, you make sure it's reasonable, that you can actually do it. So don't do something too hard for yourself. I probably wouldn't approve it anyway. So don't propose something that is outlandish. Do something that is attainable. But it's got to be complex enough to know that to show that you have some knowledge in the domain that we're talking about for that particular problem. You get 10% of the points for the proposal, 40% for the implementation, and 50% for the actual write-up. The topics we'll be talking about is search, planning, learning, and natural language processing. Those are purposely vague. I want you to do something that is interesting to you. We'll talk more about that later, but the idea here is that you should get out of this course something that is meaningful to you, and not something that where everybody is writing the exact same paper. Not to mention those are really dull to read. Discussions are another component of the course. The intent is to engage in conversation with your classmates. It is roughly 1% of your grade per discussion. So a total of 15% will come from discussions. We'll talk about the point allocation here in a moment. Uh, Whenever you do so, make sure that you address the prompt appropriately. Do review the discussion rubric. Uh, Rubrics are always a good thing. So if someone shares one with you, do go by it because they're going to. Make sure that whenever you respond to your classmates' post, you do so in a constructive and meaningful way that adds to the conversation. Don't just say, yeah, that's a great idea or whatever. Also, clearly be respectful and kind whenever you're responding to someone else as you would like them to respond to you. So be nice. So where are the points? Whenever I take a course, I always sit down and figure out where are the points at and what do I need to be paying attention. You'll notice here that it's pretty much an even split between papers and projects. And then there is a test, 5%, just because, you're in college, you got to have tests. And then the remaining 15% are coming from your discussion boards, 1 point at a time. So again, 1 point doesn't sound like a lot. Multiply it by 15, that's a letter grade and a half. So do make sure you do your discussions. Here's the current plan. Honestly, I've thought about revising this. I don't know that I will just yet, but it is a fair amount of reading because this is a large topic to cover, and I'm trying to do justice to all of the elements of this domain. So we'll start off with chapters 1 and 2, which is going to talk about basically introduction of what is AI. I'll talk about that more in a moment, and then intelligent agents. What's an intelligent agent? What's an agent? That sort of conversation. We'll move on to search in chapters 3 and 4, adversarial search and games and constraint satisfaction in 5 and 6, logical agents, first order logic and inference in first order logic, 7, 8, and 9. That's in the fourth week, and so on. I'm not going to read the entire slide to you. You can see this stuff yourself as well. You can always pause this recording as well if you want to drill into it. But as you can see by this slide, AI is a big thing. It's not one small field. It's gotten larger over time. Some of these items were added relatively recently in the past, maybe 20, 25 years. Probabilistic reasoning wasn't something that used to be part of AI, but along the way, artificial intelligence people decided, that statistic stuff, that's pretty useful. We should probably take that. And so they adopted it and brought it into this domain. Also, deep learning, reinforcement learning, those are relatively new as well. It took some algorithmic sort of advancements to enable neural networks to go beyond 2 or 3 layers and be able to handle it in an effective way, not to mention computational resources to make that happen. And then also natural language processing, definitely some advances there. Often most of it is being fueled by the actual deep learning algorithms and so on. And then we'll end the course with a discussion around the future of AI and the basically some ethics and so on. So pretty good coverage of topic. It is a big domain, lots of stuff to read, and so be prepared if you can. Try to get ahead. Um, some of the things are less important than others. We're not going to go into the weeds as far as all the algorithms and all of the analysis and all of the calculations. You do need to be able to read it and understand it, but it's not something that is essential to what we're doing here. What we're doing is a mixture at a high level, understanding what these concepts are to the point that you could actually do them if you need to. And if the point that you need to, you'll go back to this text. And part of the reason I selected this text is it's a great resource to keep around. But over time, you may, if you end up in this field, want to drill into one of these topics in greater detail than you are during this course. And if that's part of the point here is to give you that foundation so that you know where to go look. Moving on to the assignments, it's pretty much a discussion every week, except for like the final week. There's a project at weeks 3, 7, 12, and 14. Uh, a paper pretty much at weeks 5, 8, 11, and 15. Tried to make them reasonably evenly spaced so that you have time to work on them. Some of the papers and projects are a little close near the end, so you may want to get ahead. That's just something as a suggestion. It's up to you, but it's a fair amount of stuff that could come in all at once and near the end of the semester when other people may be doing the same thing in other courses. So plan ahead. And discussions for week 1, you're asked to define AI. Don't just give a kind of copy from the text sort of definition or Wikipedia, worse than that. Instead, after having listen to what I had to say, reading what you've read in the book, maybe doing a little bit of research. What does it really mean to you? What does the term mean? Make sure you list basically the subfields look a lot like the table of contents in this book, um, and discuss some real world examples that you might have seen of AI. And there are a lot of them because it is pervasive. And what do you think is pretty interesting of the topics we'll talk about, or of the topics that are in the domain? What areas do you think are the most interesting, and kind of why? Don't just say, oh, natural language processing, that's the most interesting. Why? That's the important part. One of the things that this course does is leverages resources that is by the people that developed the book. It's available at the address you see on the screen. That's AI, Modern Approach, I believe it's named after the book, Modern Approach. Yes, so they took the name of the book, abbreviated it because people at Berkeley like abbreviations. There is all of the code that is in the book, and so on, is available on GitHub. So you may want to take a look at that, especially if you want to embrace some of the examples they have and extend them. And with that, we've talked about the syllabus. I'll pause for one moment, let you collect your thoughts while I take a sip of coffee. Moving into chapter 1. Um, so the basic idea is, well, what is it? That's a good question to always ask whenever you're talking about a new field. So what does it look like in fiction, right? We've seen these things. Hopefully you've seen most of these movies. They're pretty good. Sometimes AIs are not so nice, like Terminator. Sometimes they are have their own self-interest, as in Ex Machina. Uh, Sometimes, and also an iRobot, right? So they're just wanting to get along, right? Um, Sometimes they have agendas of trying to create life and so on. I Am Mother. Sometimes they're just humorous side effects. Some of these are so. But the basic idea here is this isn't reality necessarily. So the things that are in these movies, they're plot devices, right? That's what it is. Fiction. It's not real. And we attribute to them our own projections of reality. uh, Whenever the 90s was going on, and even earlier with how it was fear, right? um, so, and then we kind of moved to a more optimistic sort of view, perhaps with Walleye or Wally. um, but drilling into what is it really, right? And the basic idea, there's kind of two schools of thought to start with. One is to make something that acts like a human. That's the Turing test, and you've probably heard of that. So that, uh, ignoring visual interactions and maybe even speech interactions, you have a device in one machine and a person in another, and the device fools them into thinking they're a person. That's the basic idea. So it's to behave in a human-like way. Uh, there's some problems with that. We'll talk about those a little more. The other approach is to do something that is rational, to to gain, or to reach some goal, based upon some desired outcome, minimizing or maximizing things along the way. So, and adapting to things that are unforeseen. That's another piece of it too. It can't just be rote, where this is the solution, so we always do this solution. There's typically some form of things that get in the way that need to be overcame. So those are the kind of two basic schools of thought. So there's fancier words for them, but at the end of it all, that's kind of what it is. Is, are they like people, or do they do things to reach some rational goal? We talk about rational decisions, and perhaps this course, as the slide says, should be called computational rationality. It's about maximally achieving a predefined goal. And it's not about how that decisions are made to reach that goal, but rather reaching the goal. So it's the end of it, not the way that you get there. So maybe a computer doesn't need to think like a person to reach the goal, and frankly, they don't. But they do need to be bounded by the constraints that the real world exists in, and reach the goals in some sort of rational way. um, and your goals, you'll see this word utility. We'll talk a fair amount about that, and it's utility of outcomes. It's about some measure of how well something meets the goal. So this and it's all about being rational means maximizing your expected utility, and that's a key concept, is doing things that get you the most or the closest to your goal or the thing you're trying to achieve. So we got this brain, so maybe we could just figure out how it works and makes computers work like it. uh, the problem is, um, first of all, we don't always make rational decisions. Sometimes we actually rationalize our decisions rather than making rational decisions. And the brain is not a simple thing to understand. It's not like there's one piece that does one thing. And in fact, it is adaptive at that, so that if something stops working in one part, it may start working somewhere else. So there's a lot of reasons that doesn't work too well. But the analogy there is pretty good. If brains are to intelligent as wings are to flight, it's a way of reaching the desired goal. And you can think of it in that whole rational versus being to where you emulate something so close to that you look like it. If you think about it from a bird versus an airplane, uh, airplanes don't fly like birds, and you would never mistake an airplane for a bird. But that doesn't mean that the goals of the airplane or the drone or any flying thing may not be able to satisfy that of what a bird does. So there's different ways of reaching the goal, and it may not be through emulation that you get there. It may be through doing it in a very different way. And then the key thing that we did learn from kind of looking at the brain and how it works is the importance of memory and simulation to figuring out how to make decisions. People do this sort of thing sometimes subconsciously, where they'll sit and visualize how something might go, think it through in their head ahead of time before they actually try to do it, potentially finding things that are going to go wrong. So that is an important lesson, and something that we may need to do in artificial intelligence. Interestingly enough, also there was a recent study that talked about perhaps computers need to sleep and dream, because that helps us as well. So while we can't necessarily straight up emulate the brain, we can be influenced by it and use it as something, as an observational sort of tool to learn from. Moving on to rational agents. So what's a rational agent? We'll talk more about that in the next section, but it's basically something that perceives and acts. It has some sort of sensors, and it may actually have actuators where it acts upon the environment it exists in. That also implies there is an environment. So there's a world or something in which it lives, and an action space where it can actually do things. Um, and this is a general kind of concept that it's been around for quite some time, is that there is this thing, and we call it an agent. And it may be a robot, and it may be just a program that's running, that does perceive and does something. It acts. And even if that's something that it's perceiving as a game, maybe it's playing chess or checkers, and it perceives the state of the board, and then it does something. And maybe it's even more abstract than that. Maybe it's a game of Pac-Man or something, where it is a computer program that is what it's perceiving, and then it's acting by controlling some of the controller. Maybe it's moving the Pac-Man around. So there are a lot of general AI techniques we're going to cover for lots of different types of problems. And the reason being is different things require different things. And in order to do some of these things, like try to pass a Turing test, requires a whole lot of other of these AI technologies, natural language processing, knowledge representation, search, all those things kind of come together in order to do that. And even this last bit is almost hinting at adaptive or reinforcement learning. So learning to recognize when and how new problems can be solved with existing techniques. So figuring out how to solve a problem. So where does AI come from? Um, a lot of places is the short answer. And it in part, it inspired by and borrows from lots of fields. We talk about philosophy, utility, and so on, things that are very much coming from that world. Neuroscience, where we've borrowed concepts related to neurons and neural networks and how we thought they work. Maybe that's not really how they work, but we kind of borrowed the concept and made it to where it was something interesting. Obviously, in order to do natural language processing and computational linguistics, you need to understand linguistics of how speech is used. Mathematics and statistics definitely in there as well. Economics, decision theory, game theory, operations research, all those things are borrowed from as well. Computer science, computer engineering, definitely in there as well. Uh, and control theory and cybernetics, especially when you start thinking about things uh, that are independent and have cost functions and so on. But definitely GPUs, field programmable gateways, all that stuff is now relevant and continuing to become more relevant because we need processing power to do a lot of this stuff in order to make it work. So the short thing is it comes from lots of places. So it is very much a broad category of things that have caused it to be, and a broad set of concepts and technologies that are used. Can't really talk about a thing without talking about where it came from. This is a rough timeline, and we'll have another one here in a little bit. Started roughly around 43 to 56. Uh, the Dartmouth workshop in 55 is kind of viewed as the main point. Almost everything we'll talk about it. 52 to 69, Lisp what came along. Lisp is an interesting language. Historically, it's probably what you would have taken as a AI language rather than Python. It is interesting. It is fun. It's harder than Python, and unnecessarily so. It's very much of a functional thing, and if you like parentheses, it's your friend. Um, then we moved into connectionist stuff early on, 66 to 73, started doing a little bit with genetic programming, kind of interesting, right? Because most people would probably think genetic programming was relatively new in the mid to late 90s, perhaps, but no, it was very early. And the perceptron, we'll talk a little bit about perceptron later on. Expert systems, 69 to 86. That's where we thought everything could be represented as a set of rules with a knowledge base and doing some inference and figuring out, you know, forward and backward chaining of how things work. Turns out not everything can be represented that way. Then 86, pretty much to present, is the neural networks came back, and this time with a passion, and didn't get really terribly interesting until around 2002 or so, whenever convolutional neural networks started becoming a thing, and we figured out how to recognize characters and numbers using kind of an interesting set of algorithms. And that led in around 2011 and so on, a true adoption of deep learning. And it is the biggest field right now inside of AI. And it's probably, whenever you ask most people what AI is, they're going to talk a bit about deep learning. Another look at the history of AI, pretty much the same sort of thing. A little bit more of some call out of some significant papers along the way. uh, and a bit more of a humorous sort of approach as well. In the 90s, we did start bringing in statistics, which was an interesting sort of merger, and also very relevant and very useful because it turns out not everything is certain. So whenever you do something like speech recognition, there's a probability associated with it of how accurate the algorithm thought it was, right? So pretty useful stuff. Looking at it visually, a slightly different sort of slide, and this I believe is taken from your text, of showing the various key sort of things along the way. Uh, so the reoccurring theme that you'll see is people losing is of interest whenever we play against a computer. So in 97, it beats a chess master. Back in 59, it beat somebody at checkers. And then goes not on here, but it is pretty relevant as well. So computers becoming at parity of people is something that we think is being important. Now, I don't know that it is, but we definitely think that way. So the key thing, though, is it's different, right? They do things in a different way than we do. But things that historically we might have done better than computers, not so much anymore. So more recent uh, beat us at Jeopardy, right? So Deep Blue beating the Jeopardy masters. You got your personal assistants, which are very much if you think about it as an agent perspective, they are perceiving the world through the wake up phrases and the words that you then say, and then they're potentially doing things, even like maybe turning your lights on and off or adjusting the temperature in your home. uh, Winning at Go, winning at Texas Hold'em, and by winning we mean beating us, right? So it's kind of interesting. Starting to drive our cars for us. Voice recognition. Microsoft recently published, I believe it was on the Switchboard data set, that voice recognition was better than human parity, which is a significant thing. In fact, the project that I'm currently working on has that same sort of goal of beating human speech recognition in the realm of transcription. So at least reaching that level, if not beating it. And in fact, the statistics we're shooting for are actually beating it. Things that also became pretty important: pay as you go, machine learning with things like Azure ML, uh, these platforms that make it easier to do uh, um, AI in general. So AutoML is a good example where it'll basically, you can give it a certain type of problem and it'll figure out what algorithm is the right one to use. So makes it a whole lot easier for somebody that claims to be a data scientist, because that's what they normally do, is figure out which one fits the best. But it does it, in a few minutes rather than days. And then also Azure started having not just GPUs, but also field programmable gateways, uh, which have brought previously unaccessible levels of performance at a reasonable cost to people. So pretty cool stuff. So talking about the risks and benefits of AI, the risk is obviously things like Skynet and Terminators and lethal drones and surveillance that is pervasive into our worlds because they can do it in a way that we can't, taking away our jobs and so on, and making sure things are doing stuff in an ethical perspective. Safety, they may actually be better than us. So there are some significant benefits. For each one of the negatives, they're not necessarily, Skynet, but in the case of surveillance, maybe it's increased safety and so on if done in the appropriate way. And employment, losing jobs may also mean improved bottom lines for organizations. So, and shifting of jobs from things that are potentially repetitive to things that are not. So we've basically went over the high level field of AI. It's not new. It's been around for some time. It is about rational actions and, or depending upon your school of thought, mimicking human behavior. Uh, there's good and bad things associated with it, and there are historically, and I kind of went over them a little briefly. There have been these things called winters, AI winters, that happen periodically, and they're periods of disillusionment with the technology. Generally, they follow a really overzealous period of AI is going to solve all of our problems. And it's historically it's been whenever it's overhyped, companies invest a lot of money into it and it doesn't pan out. They become disappointed, and all of a sudden AI researchers are looking for another jobs. So could happen again. Maybe, maybe not. We'll see. Right. Um, and there's almost always this concept of an agent inside of AI, even if it's not explicitly called out. Moving into intelligent agents in more detail. Um, so what's an agent? And basically this is kind of extending what we saw earlier, is that there is this device out there, this thing that is an agent, has boundaries, is crisp and so on, that perceives from an environment and acts upon it typically. And it perceives through sensors, acts through actuators, and typically has a certain amount of logic state, some stuff that lets it know what's going on. This is a pretty abstract sort of thing, but it does kind of get that concept across. So what's a rational agent? And it's kind of stating the obvious. It does the right thing in the context that it's in. The right thing is determined by some sort of a performance measure, some sort of function, of mathematical function perhaps. The performance measure is what should be achieved, but not how. So it is the goal, not the plan to reach the goal. Rationality, typically defined by some sort of a success criteria. Uh, the agent has sometimes prior knowledge, sometimes it doesn't. Uh, agents have actions that they can perform, and there's oftentimes a percept sequence. So they perceive things in a certain order. So there's perspective. Sometimes agents know things and sometimes they don't. Sometimes they know everything. Sometimes they only see a partial amount of the world. Sometimes the world is changing as they're observing it, which is reality, right? Most of the time, if you have things that can move inside of an environment, they're no longer there the next time you look. Information gathering is about just simply what the name says, getting information from percepts. And sometimes it's about exploration, which is sometimes there's exploitation, which is when you do things to try to benefit from what you know. Exploration is when you try to learn. And you can think of that almost like reconnaissance or something, right? So you want to figure out what the state of the world is so that you can then potentially maximize your return in that world. And doing that is about learning about environments, and typically speaking, these things are autonomous. They should learn and adapt to changes after some sort of initial knowledge and approach. They're not something that is manually controlled, because that's no longer an intelligent agent. That's like, something that you're fly by wire or something with over the some sort of connection. Environments. The different types of environments that can be physical or virtual. Task environment is a goal in place intelligence work in. uh, Performance is about performance measures, how success is measured, the environment, the world in which it interacts. Physical or logical, whatever it might be. Actuators, ways to interact with the environment. That could be a lever or a remote controlled arm. Could be turning sensor or turning valves open and closed, turning pumps on and off. Could be turning the wheel of a car, or maybe doing something with a combine on a tractor. So there's lots of ways that they can interact with the world. Uh, and if an agent is interacting with a virtual world, it's called a software agent, robot, a software robot, softbot, or something like that. Maybe just a bot. So those things do happen where the agents don't really exist per se, but they're basically software. When we talk about task environments, this is the world in which something is doing. They're either fully or partially observables. They may be able to see what's just close, or they may know what the entire state of the world is, depending upon access to the information they have. Uh, some things may not be able to be seen, so they're unobservable. Sometimes there's one agent in an environment, sometimes there's multiple, sometimes there's something in that environment that is part of the environment but moves around. So if you think of it as I don't know, we'll talk a bit about the Wampus game where you're hunting for a Wampus that may or may not be moving around. Then that's something to consider, is it's an element in the environment that may move. So not everything is stationary. Environments change. Doesn't necessarily mean it's an agent that has a set of goals and directions of itself that it's trying to achieve. Cooperative versus competitive. Sometimes there's conflict. Sometimes things will work together. Sometimes they're not. Deterministic and non-deterministic. Some things are random, some things are not. Sometimes in the real world, whenever you go to move your device with motors, things slip, or maybe they slide, or they don't go the way that they should go. So, and also sometimes whenever we're talking about non-deterministic environments versus essentially deterministic, the next state of an agent may depend upon something that's somewhat random. Otherwise, in some things, that's not the case. But if you think of a game that may have dice involved, where you're rolling dice between turns, that's non-deterministic. So it's going to be more stochastic. But if you're thinking about chess, checkers, something like that, there's no real randomness involved. Sometimes there's like duration of play. Sometimes there's sequential, where there's one decision impacts those in the future. Other times it does not, and so those are very different worlds. Um, so if you think of chess as a good example of something that has an onset going set of sequences, that are relatively long and relatively deep. Static and dynamic environment may change without the agent doing something, uh, or may not. So if it's static, it's not going to change without them interacting with it. If it's dynamic, it may be changing on its own, or it may be semi-dynamic where it doesn't change, but maybe the performance score does. So maybe there's time involved or some other factor that figures into it. Known or unknown. Sometimes the agent knows the rules of the environment, sometimes they don't. Sometimes they have to figure it out as they're going along of what they're allowed to do and what they cannot do. So a good example of an agent, a true agent, is like a Mars rover, right? It's running a significant delay time away from us, so we don't always have access to them. So they have to be very independent. It's a mixture of a program plus an architecture. The program is implementation of the agent's function. The architecture is the computing platform that it runs on. That's going to include things like sensors, actuators, motors. Might just be a PC, and it might be something like a Mars, rover. So the the concept here is that it's a combination of things that go together, and they're of varying degrees of complexity, but they do have some things in common. So drilling into the various types of agent programs, um, and this is basically the concept, as we talked previously about, is they take input and they return actions to actuators, and they may maintain history, right? So drilling in to a simple reflex agent, almost the simplest one, and we've kind of talked a bit about that, sort of, in a way, but there's basically a set of rules which determine actions based upon a combination of the environment, of what it's sensing, and where it's trying to go. So you have something out here that is reading from the sensors, keeping track of the current state, figuring out what rules are applicable, to figuring what to do, and then acting upon it. Relatively simple. Doesn't necessarily keep track of what it did in the past. A goals agent, much more complex. It's got a desired state or outcome it's going for. It's going to have to search for ways to get there. It's going to plan potentially a sequence of actions to reach that goal, and may or may not be all that efficient because it may have to spend some time coming up with longer ways of doing stuff. A key thing is it may very well remember what it's done and determine the impact of possible action. So it may keep track of, when I did this, this happened. So maybe it's a good thing or maybe it's a bad thing. So it can lead towards a bit of learning. And then similar in a way is around utility based agents. This is about some sort of a utility function that determines good or bad. So sometimes you're wanting to maximize the utilization rate. Sometimes you're wanting to lower it with a minimization effort, depending upon what the situation is. And then there's this concept of an expected utility, which is what you think will happen, and then it may or may not really happen. So there may be the real utility that is realized by having done something. It may not include a model, and that's when you went into the realm of reinforcement learning. Is there's not necessarily a predefined model that controls how things are going to behave. It figures it out on the fly based upon what it observes. And then the kind of the last bit is the learning environment. So you basically receive, somebody is critiquing things, providing feedback, doing a bit of learning, calculating some performance, figuring out the problem, and so on, with the goal of trying to reach, your desired state. More complex, um, uh, and may or may not be effective depending on what the situation is. Then we talk about, how do you represent an environment? Um, could be state discrete, could be factored, could be structured with hierarchies and so on. The greater the expectiveness, the expressiveness, the higher the fidelity, but at the trade-off of potentially greater storage and constraints often figure into that around capabilities are available to you to store things. Um, a localist representation, one of the mapping between concept and where it is stored, and a distributed representation where there's multiple sort of concepts stored in multiple locations that represent the single thing. And with that, we've pretty much covered the topics in chapters 1 and 2. If you have any questions, do reach out to me. That's what I'm here for. I look forward to speaking to you in the remainder of the course, and stay safe, and we'll talk again next week.